looking at the symmetry, which is a property of a graph. So for a graph to be symmetric with respect to the y-axis, the point negative xy must be on the graph whenever the point x and y. So again, symmetry, remember, you studied that a long time ago, maybe 5th grade or something. But symmetric with respect to the y-axis, if a point is here, then it has to be here. That's what symmetry is, right? So if the point x, y is here, then we have to have the point negative x and y. For the same reason, symmetry with respect to the x-axis is the opposite. The point, if the point x and y is there, then the point x negative y should be there. What's nice about it is that how do we figure it out? Is by the following: the graph of an equation is symmetric with respect to the y-axis if the replacement of x with negative x result in an equivalent equation. So remember, now we're not talking about looking at the graph, we're trying to look at an equation and wonder, does that equation have any symmetry without graphing it? So what we do is the replacement of x with negative x. So if you replace x with negative x and the equation is still same as what we started with, then we have symmetry with respect to the y-axis. And the opposite, symmetric with respect to the x-axis if the replacement with of y with negative y gives you the same thing. Now we have one more symmetry, and that is symmetric with respect to the origin. A graph is symmetric with respect to the origin if a point here, x and y, then the point negative x, negative y should be on the graph. Okay? It could be anything. So that's what we call symmetric with respect to the origin. It's like a 180 degrees around the origin. So the replacement of both, and both is an important word here, both x with negative x and y with negative y gives you the equivalent statement. So what's nice about the symmetry is the following. A graph that is symmetric to x and the y-axis automatically is symmetric with respect to the origin. Also, it turns out to be that any graph that possesses any two types of symmetries must have the third kind. I love to demonstrate in this scratch paper. So let's say we have this, just a graph, a small one. Let us assume that this graph has symmetry with respect to the y-axis. That means whatever here should be also here. And let's say also it's symmetric with respect to the x-axis. That means whatever up is down. And now you'll see that this is symmetric with respect to the origin. Let's take another example. How about like this? Let's say that we say that the graph is symmetric with respect to the origin, meaning whatever here should be also here. And also let's take another symmetry. So we did origin, let's say y-axis. So whatever on the right should be on the left, and whatever left should be on the right. You'll see that it's automatically symmetric with respect to the x-axis. So let's do an example. There's only one example we're going to do with few parts. So you have to show your work here. You're not doing it by graphing. So let's test the symmetry. So let's see. To test for the x-axis, we're going to replace y with negative y. Now, is this equivalent to this? Yes, of course, because the absolute value of negative y is y. Let's check the y-axis symmetry, meaning replacing x with negative x in the original. Now, is this equivalent to this? No, because this is negative. Should I test the origin? The answer is no. Why? Because it can't be true. If it's true, then it has to have all three. Let's try it again. Let's test the x-axis symmetry, meaning replace y with negative y. Now, is this equivalent to this? Let's say you're not sure, like here. Just multiply the whole equation, because we say equivalent. Multiply by -1 to get this. Again, now look, is this equivalent to this? Absolutely not. Let's try the y-axis symmetry, which is replacing x with -x. Now, is that equivalent to the original? Of course, because the absolute value of -x is x. So do I need to test the origin? I hope you said no. Okay. Let's check this one. Let's check the x-axis. The work is easy, guys, but you have to show your work. For the x-axis, I'm going to replace y. Let's replace y with -y. So instead of y, -y. Now, is this equivalent to this? Absolutely not. Let's try the y-axis, meaning replace x with -x. So it's going to become -2x, positive y equals 6. Now, is this equivalent to this? No, they're not the same equation. Now, let's try the origin. Origin replacing x. Okay, we didn't write origin. Replacing x with -x and y with -y equals 6. Is this equivalent to this? Absolutely not. The right-hand side should have been -6 for it to be equivalent. So here we have none. I'll let you do this. Okay. Replace. No, this is not the one I want you to do it. Let me do it. X-axis. Replace y with -y. Well, when you take the -y and square it, you're going to get the same as the original. Y-axis. Replace x with -x. Same reason, when you take -x and square it, you're going to get x squared, so that's equivalent. Should I test the origin? No, it's already, if you have any two, then it's automatically the third. So this is all 3. Okay. Let's see the next one. Let's check x-axis symmetry. Replace y with -y. These are definitely not equivalent. Let's test the y-axis symmetry. For the y-axis, you replace x with -x. Remember now, this -x is raised to the 3rd power. So this is going to be -2x cubed. Is this equivalent to this? No. And now we're going to test the origin. Replace both y with -y and x with -x. So you're going to get -y equal to -2x cubed. Multiplying both by negative, you're going to get the original. So we have only the origin. I'll let you do the last one. Here's a nice summary of what we just did. Noticing that any symmetry with respect to the x-axis will not result in a function, because remember, for a function you have to have the vertical line test. And what's nice about symmetry with respect to the x-axis, it kind of looks like the x squared. This one kind of looks like the x cubed. So the power of the x is easy to remind you of which symmetry we're looking at. The last thing is even and odd functions. So now, if not equation, a function. So we cannot use that. That is symmetry with respect to the x-axis does not produce a function. So let's look at this. A function is called an even function if f of negative x equal to f of x. In another word, look at what we did. We replaced x with negative x and we got equivalent equation. Do you remember what that was? That was y-axis symmetry. So if the graph has a y-axis symmetry like this one, then the function is an even function. A function is called an odd function if f of negative x is equal to the opposite, the negative of f of x. Let's see what you did. You replaced the x with negative x and the y, which is the f, all of it with negative y. And that is symmetric with respect to the origin. So let us see how easy it is to do these examples of odd and even. Again, you have to show the work. All you need to do is find f of negative x. If it's equal to the original function, it's even. If it's equal to the opposite of the original, it's odd. If it's not this or that, it's neither. So we need to determine whether each function defined is even, odd, or neither, showing the work. So what is the work? Replace x with negative x, meaning find f of negative x. Well, this is going to be negative x to the fifth plus 2 times negative x to the third minus 3 times negative x. Well, all of these are raised to an odd power, meaning the negative is going to show, it's going to stay. Minus a minus is positive 3x. And ask yourself the question, is this equal to the original function? No. Is it equal to the opposite of the original function? Let's see, negative, negative, positive. Yes, so that is an odd function. Let's do this one. What is f of negative x? Well, I'm replacing each x with negative x, which what will it give me? Because this is raised to the fourth power, this is raised to the second power, both are even power. I'm going to get 2x to the fourth minus 3x squared plus 3, which is equal to the original function, so that's an even function. The last one, f of negative x is equal to negative x squared plus 6 times negative x plus 9. So this is equal to, this is squared, so this is x squared. 6 times negative x is negative 6x plus 9. Now, is this equal to the original function? You'll see it's not because of that. Is it equal to the complete opposite of the original? No, because this is positive and it's positive. So here's the neither.